Hello, everyone, and welcome to our first webinar here of 2021. This is How to Engineer Software Part 3 with Steve Tockey. If you'd like to catch parts 1 and 2 later, I'll go ahead and link them in the chat after I introduce this webinar. Today's webinar is presented by Steve Tockey. He's the principal consultant at Construx and the author of How to Engineer Software, which this webinar is based on. Today we'll have a brief Q&A at the end of the presentation. Feel free to submit your questions throughout and I'll queue those up for Steve at the end. I hope you find today's webinar valuable and share it with your peers. And I'll be sending a link to the recording within about 48 hours after it has ended. Steve, thank you for being here. I'll go ahead and turn the time over to you.
Okay, thank you, Jesse. Hello, everyone, and welcome to part 3 in this series. Part 1 was an overview of semantic modeling and model-based software development. Part 2 was a deeper dive into semantic modeling, talking about the content and why should you care. And now for part 3, we're going to get into starting with the semantic model, deriving design and code from the semantic model, because after all, if it doesn't lead to executable code, of what use is it? And you're going to see how this leads to directly to executable code. Obligatory legal stuff, fine. And so my goal here is to show how design and code can be derived from a semantic model, quite directly, I might add. And I want to illustrate more the value of semantic modeling. Earlier, we were looking at the value in terms of helping us straighten out the requirements, make sure we've got complete requirements, make sure we've got unambiguous requirements. And now we're going to build on that in terms of its value for design and coding. Now, I am going to do some derivation of design and code using an example, but I do want to emphasize that this is only an existence proof. I'm going to show you one way of turning the semantic model into design and code, but this is just one of many ways. Don't think that this is the only way of doing it. I'm going to prove that it can be done, and I'm going to show you how easy it can be, but it can be done other ways. Hopefully you'll be able to see that as we go. Now, just as a reminder, remember why we're doing all of this is that my experience is that there are 5 root causes of poor software project performance. Projects are chronically late, projects are chronically over budget, we don't deliver everything we're supposed to, etc. And again, vague, ambiguous, incomplete requirements being number 1, inadequate project management, number 2, lack of planning, lack of tracking, lack of change control, lack of risk management, etc. Uncontrolled design and code complexity, overdependence on testing, leading to very high rework ratios, and self-documenting code is a myth, which is not a development issue per se, it's a long-term maintenance issue. Linked in the description will be a link to the video Top 5 Challenges in Software Development, which was done as a lunch and learn several months ago, that will go into these in much more detail, just to, if you want to track down and get that detail. As well, if you want to go look at part 1, if you haven't seen part 1, semantic models overall, that will be linked in the description. We talked about the whole series of things that we build, the semantic model being one of those things. We're not going to be looking at the background today. We're not going to be looking at the interface specification today. Our focus will be on the semantic model, not as the end product, but the input, and then the software design and the source code as the output. And again, if you remember the whole idea about engineering being dependent on economics, the monopoly money is there just to remind you that as long as we're doing all of this, keeping the economics, the investment, the return on investment in mind, then this is one of the ways that we qualify as a true engineering approach to software development. Again, I want to reference the part 2, deeper dive into semantic models, that again, as a reminder, just remember that all non-trivial software exists to enforce some set of business policies, using the term abstractly or somewhat advisedly, and then carry out business processes. So remember, if we were talking about being a bank, what does it mean to be a bank customer? What does it mean to be an account? Can I have a customer without an account? Can I have an account without a customer? Can a customer have many accounts? Can an account have many customers? What are the valid business states of an account, et cetera, et cetera? That's all policy. And the bank software is there to enforce those policies. Just as well, there are processes along the lines of open an account, put money into an account, take money out of an account, move money from one account to another. And so what we're dealing with here in semantic modeling is a highly specialized dialect of UML, UML Unified Modeling Language. There are no bits, no bytes, no database tables, no stored procedures, no microservices, no tasks, no threads, none of that. It is purely an expression of business policy and business process, where we have business process at multiple levels of detail. And if you remember from the part 2 deeper dive, the example that we were using was a miniaturized Amazon.com. It was called order fulfillment. So again, I just want to touch on that as a reminder. This is high-level business process. I have actors and I have high-level business processes. Customer, I want to see what's in the catalog so I can decide what to order. Customer says, I want to add something to my cart. I want to drop something from my cart. Show me what the status of my order is right now. I want to check out. I want to cancel an order. And then the warehouse worker needs to know which orders are packable. They need to pack an order, ship an order, et cetera, et cetera. So very high top level business process. Business policies, again, expressed in terms of a logical, if you will, data model. Can a customer not have a book order? Can a book order not have a customer? Can a book order have many customers? Can a customer have many book orders? These are the kind of business policies that are being expressed here. Though remember that we go a layer of detail, a layer of depth underneath this. So we'll have class descriptions for each of these classes that give us more detail understanding about what these classes mean. We'll have attribute descriptions. What does it mean to be a date opened on a book order? What does it mean to be a shipping address on a book order? What does it mean to be a selling price of a medium? And again, remember that we were talking about exposing all kinds of otherwise hidden requirements when we were talking about the range of these attributes. A date opened can't be a date any earlier than, let's just say, January 1st of the year 1990, and it can't be any later than today. The selling price can't be any less than $1 or 50 cents or whatever, and it can't be any greater than maybe $1,000. With the idea being is that by exposing those ranges, we're flushing out business constraints, requirements. These are functional requirements that would otherwise be totally missed on a typical project. So the developer would implement date opened in terms of, say, Java date or C++ date, which supports a wider range of dates than are actually valid for order fulfillment. And so we want to communicate what those business constraints are so that the developer actually implements those constraints. Otherwise, it's a defect in the software. And again, intermediate level process, if you remember the use cases, open an order, add to cart, what's in my cart, et cetera, et cetera. This is an intermediate view of business process, and conceivably we would have one sequence diagram for each of those use cases. At the high level was just saying there was a business process. Here we're looking at that process from an intermediate level. And then in terms of detailed business process, we are having these UML state charts. What business states could something be in? What business events does it need to be responding to? If it's in this state when it sees that event, then what is its response in terms of making a transition, carrying out an action, etc. And again, there's more depth to here. This is only the picture part. we need to talk about, or we have the option of providing state and event descriptions to add more detail. But as well, we would have action specifications. So if I am an open book order and I'm told to add, what does it actually mean in detail to add a line? If I am an order which is packed and I am in a packable condition, and I'm a placed order, I see a packed event, I am packable. As I make the transition from placed to packed, I carry out this action mark as packed. Well, what does that mean precisely? And so each of the actions would be specified. And I'm showing you here two of the state models, state charts, if you will, for classes in order fulfillment. Of course, there are more, but just to carry out, to get across the idea of specifying business process at a very fine-grained, a detail level. And so again, this is the input. If you want more depth, more description of what's in a semantic model, then again, go back to part 2. It will be linked in the description. Okay, so we're going to take this as input now. And remember from part 1 that code is a mapping. Code maps the semantic model of the business onto the semantic model of the technology. There are business semantics that are captured in the semantic model, but there are also technology semantics. What does it mean to be a Java class? What does it mean to be a Java instance variable? Can I have an instance variable without a class? Can I have a class without an instance variable, et cetera, et cetera? That what code is actually doing is taking elements of the business semantic model and mapping them onto elements of the technology semantic model in a way that is sufficiently complete so that everything in the semantic model that the business wanted automated had to have gotten mapped, otherwise it wasn't automated. But we need to preserve the business semantic so that when we're doing the mapping of deposit and the bank account, we had to map deposit onto addition, not multiplication, not subtraction, not division, because addition in Java had the right semantic. And again, satisfy the non-functional requirements. It all had to be accurate enough. It had to be scalable enough. It had to be fast enough, etc. And I just want to point the link here at the bottom. Again, it will be linked in the description. But the point is, you can find at that, it's a Dropbox folder, but there you will be able to find the complete semantic model for order fulfillment, and you will find the complete executable code for that implementation of order fulfillment. So you'll be able to see, on the one hand, here was the semantic model that came in, and on the other hand, here is the code that came out. And you'll be able to see in detail from end to end how the semantic model turned into code. I'm only going to be sampling little bits and pieces of it here, but if you want to see the whole thing, there it is. Okay. So now the outline, the process, this is the important thing, the process. There are many ways that I can start with the semantic model and translating to design in code. I'm going to show you a way that is object-oriented. I'm going to show you a way using Java. But if you're using Python, for example, the mapping would be different. The process would be in some ways definitely at a detailed level different. If you're going to do this in take the semantic model and implement it in C, for example. You can certainly do that, but the process would be different. I'll give you at least an overview, a hint at what the process would look like later. So these are 7 steps for one way of translating a semantic model into, for example, Java code. You don't have to do the steps necessarily in exactly this order. But whatever, this is a convenient order, and so off we go. At the top level, we're going to take the classes in the semantic model and the associations, and those will become classes in the core of the design. Now, I need to point out that I am making an assumption here that we're using a model view controller kind of architectural style. The top level architecture of this system is model view controller. And basically what's happening here is that the semantic model essentially drives model region in the model view controller architecture area. Okay, and so view and controller would be driven by the interface spec, but we're not talking about that today. The messages and the sequence diagrams of the semantic model become operations, or what you might call methods, but that's using the term somewhat incorrectly. More on that later. You're going to see as we go through this a heavy dependence on something called design by contract. What does it mean? Why are we doing it? We'll touch on that later. But knowing the classes in the design, knowing the operations in the design, I worry about the contracts for those operations, and I'll show you how we can derive them from content in the semantic model. Then the attributes need to turn into instance variables, and the associations will then further turn into instance variables. And then we'll finish the operation signatures. Now, what I mean signature here, I mean the name of the operation, the function, I mean the number of parameters, and I mean the data types, the types of the parameters. And again, that'll become more obvious as we go on. And then finally, the last thing we're going to be looking at is, given all of the above, developing the method level implementation, the code between the curly braces based on all that we've done so far, and making the code actually executable. Okay, so step one was to take all of the classes in the semantic model, turn them into classes in model region of my model view controller architecture, and at the same time take all of the associations. And so if you were looking side by side with the class model in the semantic model, the class diagram in the semantic model, and looking at this as the model region design in view controller, you would see exactly a one-for-one correspondence. Customer over there became customer over here. Title over there became title over here. Book order over there became book order over here. And so part of the point that I want you to pay attention to is, on the one hand, how mechanical this process is. It doesn't take anybody a huge amount of intelligence to be doing a lot of this. The other is that while this is a relatively small semantic model, that the semantic model could be arbitrarily large, and we could still follow the same process and end up by a straightforward sequence of steps from a very large, very complex semantic model with large complex code that implements that semantic model correctly. Now, the last thing I want to say here is simply that the shaded ones are the ones that got mapped over because they were associations. But for right now, they're going to be placeholders because there's a number of things that we could do with them later. I just keep them now as placeholders, and we'll do a final disposition of them later. So they'll keep around, but we're going to do something with them later. We don't know enough right now to know what we're going to do later. So as I said, again, they're just placeholders. Okay, step two was that all of the messages that were in all of the sequence diagrams in the semantic model need to turn into these operations. Now, just to be really clear about vocabulary, we use the word, in industry-wide, we tend to use the word method kind of indiscriminately, and that ends up being a little bit of a problem, as you're going to see. And so the OMG, the Object Management Group, the people that brought you UML, in order to help emphasize the importance, the role of encapsulation that we're going to talk about in just a moment, they use a vocabulary where an operation is the external view. You're outside of a class, there is some function on the interface. The operation is what you see on the interface. The method is the implementation of that thing under the covers. And again, for encapsulation reasons, we want to have a vocabulary that says, when I'm talking about the operation, I'm talking about how people see how they see the existence of this function, and its interface. Now, the method, again, is the inside. How did we actually write lines of code that implement that? Operation external view, the method internal view, and we want to encapsulate the method. And so the vocabulary here is just to make sure which side of the encapsulation barrier that we're on. Okay, so somehow or another, each of those messages that when we were back in the semantic model, remember all those messages were net flow of information. The source knew something. The destination needed to know that in order to get its job done. When and how did the information get from the source to the destination? Well, that's a technology issue. That's a design issue. And so now we're going to look at making decisions about how and when to get some information that's known in some source to some destination. And I'm going to introduce the idea of pushing or pulling, P-U-L-L, pull, okay? And so the semantic model perspective was what I just showed you on the previous slide. What I'm showing you here is the design perspective, with the top layer being the push layer. If I can use the terminology master slave, client server, in this case, the source is the client and it is pushing the information into the destination, which induces the need for an operation on the interface of the destination. And so you're seeing in the high level design on the left side, and you're seeing the design sequence diagram on the right side. The source says, hey, I've decided that it's time to tell you the information. I'm going to push that information into you by invoking this put information operation. The destination does what it needs to and returns. Again, the source is the client, the destination is the server. But just the same, we could pull, we could turn it around. We could make the source the client, the destination the server. And so the destination says, hey, it's been a while since I've seen what that information was up to. I better go see what it's up to now. So it uses a get information operation on the source and says, hey, tell me. And so again, the destination is the client. It says, hey, source, tell me. Source says, here's what's going on right now. And so while the net flow of information is the same from source to destination, net flow of information is the same, the control flow is 180 degrees opposite. In one case, source is client, destination is server. In the other case, destination is client and source is server. And so you see that for every single communication, for every single message in the semantic model, I have an option of implementing it in terms of push or implementing it in terms of pull, which means that at least theoretically, the total number of possible designs is on the order of 2 raised to the power of the number of messages. And so if there happen to be 100 messages that were floating around in the sequence diagrams for the system, that would mean I would have on the order of 2 to the 100th power potential designs in terms of who's client, who's server, who's pushing, who's pulling, et cetera, et cetera. Now, in reality, in practice, life can be a whole lot simpler. Normally, what we're going to do is push events and pull data. If it is an event message in the semantic model, the class that signals the event will be the client, and the class that responds to the event. In other words, it has the event on its state diagram. It will be the server, meaning that the operation belongs on the responding class. Where if it's data, there is some data that's known over there. It's not an event, it's just data. What is the status of the order? What is the ISBN of a title? What is the price of the title? That, if you will, static data, the class that's providing the data will be the server, the class that needs the data will be the client, and the operation will be on the class that owns that data. So basically, again, very simply, push events, pull data. This leads to the most synchronous design. It's the easiest to implement in most object-oriented languages like C++, C#, Java, et cetera, that by changing from not always pushing events, sometimes pulling events, and changing from not always pulling data, sometimes pushing data, that leads me to a more asynchronous design that may be appropriate given some technical and economic circumstances, but it does make it more complex. It's more asynchronous, wonderful, it's just more complex. So for purposes today, I'm just going to do the simplest, most synchronous design, and we're just going to push events and pull data. I'm not forced to do that in all cases. I'm just going to do it in this case because it's simple and easy to follow. Okay, and so if I look at a sequence diagram for packable orders, on the top layer, that's the sequence diagram for the semantic model. That was my input. Now, again, I want to point out that stock level is an attribute of print medium that is an order line packable. That's what's known as a derived attribute on a book order line. There's a formula that figures that out. And then book order, if the order is packable, again, that's a derived attribute. So these are all attributes. They're all data. We're going to pull the data. And so that induces the need for a stock level getter on print medium and is packable getter on book order line, and an is packable, which returns true and false, getter on book order. So that when Al, the warehouse worker, is asked, what are the packable orders, that function needs to go out and literally query every order and say, are you packable, are you packable? And then for the list that are packable, return that back to Al, the warehouse worker. Again, on the top, it's the semantic model. That is the underlying business semantic, where there's no bits, no bytes, no database tables, no stored procedures. But you see on the bottom, that is the technology version. We have mapped those business messages onto getters in the design. And so the bottom, again, is the design sequence diagram. Now, if I take all of that from the design sequence diagram and I forward it onto the design class diagram, then the shading is showing you, oh, okay, so I need a stock level getter on print medium. I need an is packable getter on book order line. I need an is packable getter on book order. And I need a packable orders getter on the warehouse worker class. And so that was all rather straightforward, not a problem. So we move on. And let's talk about the sequence diagram for packing an order. Now, in the semantic model, it's a complex enough business process that it had to be spread over a pair of semantic model sequence diagrams. So this is just the first half of this. Al, the warehouse worker, says, hey, this order got packed. The book order needs to know that. And when the book order knows that, then the order lines in the order need to know that they got packed, et cetera, et cetera. But these are all events. Packed is an event on the state model of book order. Packed is also an event on the state model of book order line. Picked is an event on the state model of print medium. But since these are all events, then what I need to do is push them. And so if I go from semantic model sequence diagram to design sequence diagram, I am pushing those events. Okay, great. The other half of this semantic model sequence diagram, if the print medium had its stock level go below a certain level, then we had to do some replenish ordering that involved the title and the publisher, et cetera, et cetera. But again, this is all event communication. And again, we're pushing events. And so from a design perspective, now we're pushing events. And so again, just a quick review and emphasize that the semantic model sequence diagrams are all in terms of net flow of information. Who knows the information, who needs to know in order to get their job done. The design sequence diagram is flow of control. Who is client, who is server, who is master, who is slave, who is saying when it happens, who responds. Again, the operation goes on the responder. So again, if I forward those induced operations off of this sequence diagram, the shading here will show me which new operations on which classes. And oh, by the way, the abbreviation CTOR paren, CTOR, that's just a C++ abbreviation for a constructor, so you don't get too confused. And so all I need to do is look through all of the sequence diagrams for all messages. And again, just apply the rule of pushing all the events and pulling all the data. And when I'm done with that, I end up with, oh, well, here are the classes and here are the operations that need to be on all of those classes. And so I've got a fair portion, not complete, but I've got a fair portion of the design already essentially mechanically derived, extracted from the semantic model. Now, of course, there's a lot more to go. We're not done yet, but we're a fair part along the way. Okay, so next up is to again remind you of that deliberate encapsulation barrier. A very important part of good design is encapsulation. And so let me be really obvious here. If I am the person who's responsible for designing and implementing book order, and book order, as you see here, involves using the class book order line, then hugely importantly, I, in class book order, need to be able to do everything I need to do with book order lines simply by looking at the high level design, simply by looking at the interface for book order line. There should be no reason why I would ever want to go look at the implementation, the method level, the internal instance variables, methods, all of that kind of stuff. No, because that completely breaks encapsulation. Similarly, book order line, if my responsibility is to implement, design and implement book order line, it's in terms of class medium. I should be able in book order line to do everything I need to do writing code for book order line through the interface of medium. And the whole reason here is to help manage complexity, which remember the number 3 root cause was complexity gets out of hand. And one of the reasons that complexity gets out of hand is that we violate encapsulation. We expose things that should not have been exposed. And so there's a very deliberate encapsulation barrier here in the design. The high level design is that encapsulation barrier. All of the underlying detailed design needs to be hidden. There's no need for somebody over here to know or even care how that other thing is implemented. We need to develop to an interface. We're not developing through an interface. And so in other words, the one who wants to use the other class needs to know the syntax, the signature of the operation. What is the name of the function and what is the number and types of the parameters? However, that alone is not enough. I also need to know the semantics. I need to know the behavior. And in order to expose the behavior without exposing the underlying implementation, that is where design by contract comes in. And so if you're familiar with design by contract, great. If you're not, there's lots of references to it, both on the web and written papers, whatever. But a function needs to be understood and specified in terms of a contract. And this is the semantic of the interface. So just to be obvious here, public void open paren double initial amount close paren. That is the signature of the function. That's the signature. That's the syntax of the interface. Any programmer anywhere writes a line of code calling that function that complies with that syntax. The compiler is happy, the linker is happy, etc. But that function also has a semantic. It has a behavior. What happens when the initial amount is less than 0? What happens if the initial amount is greater than $100,000? We need to communicate to the caller. We need to communicate to the person who's writing code to use this operation What things need to be true before you call this operation? And that's the requires part of the contract. And the guarantees part says, so long as you satisfy the requires part, then here's what I promise to do for you. So as I said, the contract is the semantic of the interface. And if I didn't expose the semantic of the interface of that operation, then I must force you. Your only alternative to understand how that function behaves is to go read the lines of code between the curly brace. And that's the last thing I want you to do. Because if you write your client code with full knowledge of how the server code is working, that prevents me from going in on the server code, making a change, because you are depending on this code being implemented in exactly that way. I changed it and I broke your code. And so the point then is you write client code to this syntax and semantics. I write the implementation to the same semantic and the same syntax. I am free to change the implementation in any way I want to, so long as it doesn't change the semantic, so long as it doesn't change the contract. And if I do that, change the implementation in any way that does not change the contract, then I guarantee that I didn't break your code. And so the whole point in all of this that I would love to spend more time on, but we can't. But the bottom line is that without design by contract, there can be no encapsulation. And for an industry that talks about as much encapsulation this, encapsulation that, encapsulation here, encapsulation there, when I go look at the actual designs and codes, I'm not seeing contracts. And so that's a clear contradiction. You cannot encapsulate without doing design by contract. So I just, again, want to make sure that everybody's aware of what design by contract is and why it is so important. Because without it, I don't get any encapsulation, and that's really key for managing complexity. Okay, so if I have an operation that's there to implement pulled data, just as we were doing earlier, then it could be an operation that's reading an attribute where, for example, it might be reading the status of an order. It might be looking at the quantity on a book order line. It might be looking at the selling price of a media. It might be looking at the stock on hand for a print media. That the contracts for those are really very simple. They don't require anything, and they guarantee they give you back what you asked for. The derived attributes are a little bit more complex, in that certainly they want to guarantee that they give you back what you were asking for. But and by the way, book order is packable, is a derived attribute. Book order line is packable as a derived attribute. Those don't have any input parameters. But one of the things that we didn't talk about that's part of the semantic model is that the manager needs to know the sales results. And in order to figure out the sales results, that involves a date range. For sales starting on what date, ending on what date. And so the operation sales will have a starting date parameter and an ending date parameter, but are there constraints? The starting date can't be any earlier than, the ending date can't be any later than, et cetera, et cetera. So there may be requirements on the contract for a derived attribute because there could be some input parameters. Okay, and so that was kind of abstract. Let's get concrete. And so on class book order, then the getter that exposes the book order status, the contract is, there's no requirement. Call this guy at any time, and the result will be you will get back the value corresponding to the current state of that order being returned. Now, I'm declaring the type to be TBD right now, because that's a later step where I assign data types to things. So for right now, I don't know the data type. It's TBD. We'll resolve that later. Just the same, is this book order packable? The data type is TBD right now. Now, fairly obviously, in the end, it's going to be some kind of Boolean. But for right now, just to be consistent, I'm just leaving it as TBD. This function doesn't require anything. Call me at any time. And what comes back is the value true when the state of the order is placed and each of the lines in the order is packable, then it is a packable order. If its state is not placed, or any of the state is placed, but any of the lines in the order is not packable, then the order as a whole is not packable. And so notice how I'm defining a semantic to the interface for these getters. What do they require? Nothing in this case. What do they guarantee? You get this information back. The underlying implementation, how do we figure out if an order is packable? That's, again, to be encapsulated. The contract allows me to encapsulate that. Okay, now, on the other hand, if the operation was there because of a pushed event, this is maybe somewhat complex, but let me walk you through it. This is sort of the worst case. In all cases, the contract for an event communication will be some variation on the same basic theme. The top layer is the semantic model. The bottom layer is the design and code. Okay. On the left-hand side is high level, and on the right-hand side is detailed. So what you're seeing, upper right corner, upper right quadrant, is a fragment of a state model that says, if an event 1 happens while we're in state 1 and we're doing activity 1, then what we have to do is stop doing activity 1. As an exit action out of state 1, we need to do action 2. As a transition action on event 1, we need to do action 3. As an entry into state 2, we need to do action 4. And as long as we're in state 2, we need to continue doing activity 2. Okay, so that's just shading, is showing us a fragment of a state model for a particular class in a semantic model. Fine, but because that is the state model, then objects of class X need to respond to event 1s, objects of class X need to respond to event 2s, and the sequence diagram that's in the upper left quadrant is just showing me where the event 1 came from and where the event 2 came from. Okay, but if I go upper left to lower left, again, my initial design, class X in the semantic model became class X in the design, class Y, class Z. But because event 1 was an event message that induced the need for an event 1 operation on class X in the design. Okay. But if I'm looking at the lower right-hand side, then understand that on class X, there is a method, an operation that's an event 1. The name of the operation is the name of the event. That here is its contract. Event 1 requires that the starting state be state 1, and it guarantees that activity 1 got stopped, action 2, action 3, action 4 have happened, activity 2 has started, and now the state of the object is state 2. And the important point is that the semantic that's expressed in the contract is exactly the semantic that's expressed in the semantic model. And so because the semantic model state chart looked like this, then the high-level design had to look like that, and the detailed design had to look like that. And so literally it's a mechanical process that enables me to derive the contracts for the event operations by simply looking at starting state, what transitions, I'm not showing it here, but there's something called a guard in UML that factors in here. But again, it's literally a mechanical process. Now, this is abstract, this is high level, this is worst case if I want to get concrete. Then specifically for class book order for method place, then on the left hand and the top right, that's all semantic model content, all of that continuously shaded stuff that starts with the state model, all the stuff that's shaded in the state model, and then the upper right is the action specification for the action mark as placed. What you're seeing on the lower right is, again, the signature, public void place, some data type to be determined later, an address. And because the semantic in the semantic model is you can only place an open account, an open order, if the order does have print medium, then it gets marked as placed and becomes a placed order. But if that order is open and it doesn't have any print medium, it's all ebook medium, then it gets marked as placed and the order becomes completed. Then you can see that very same business semantic being expressed in the contract. Because the semantic model looked like this, the contract had to look like that. It was a very mechanical translation. Okay, fine. Now, again, I could do that for all of the events. So if I'm looking at an operation, public void cancel requires that the state is placed, guarantees that the state is now canceled. Public void packed requires that the state is packed, public void shipped. I'm getting out of sync here. Public void shipped requires that the state is packed and guarantees that the state is completed, et cetera, et cetera. Okay. Next, I want to be looking at taking the attributes that are in the semantic model and turning them into instance variables in the design. And so for every semantic model attribute, understanding what its range is, then I need to represent it using some appropriate runtime type. Now, in some cases, I'm just going to use a built-in runtime type, like int, like float, like double, like char, like string, like date, etc. And if I can use a built-in data type, that's wonderful. But there are cases where I can't use a pre-existing built-in data type. I have to build my own implementation, like money, like a constrained date, no earlier than, no later than, like a composite structure, like an address. And basically the point I'm making here is that decision is based on essentially what are we doing with that data? Are we doing computation on it? Because if we're doing computation, then I want to store it, represent it in a computable form, int, float, double. Okay. If I'm only storing it and retrieving it for display, then I want to store it in a retrievable, a presentable, like a string, et cetera, et cetera. And so some examples here is that in the semantic model, class title had a copyright year that for reasons that we could go into at some other point in time would be a string. The stock level on a print medium would be most obviously an int because it is something that is computed on. The copyright year is only ever displayed, stored in an easily displayable format. The stock level is computed and so stored in a computable format. The date opened of a book order ends up having to be constrained beyond just normal date. So the idea here, class WB date, web books date, is a wrapper around standard date that enforces a no earlier than, no later than kind of constraint. Okay, and so what I'm showing you here is that for all of the attributes that were in the semantic model, having made choices of use a built-in type, use a custom type, et cetera, and so all the shading here is for the instance variables in the detailed design. Okay. Step 5 was to say, well, remember those association placeholders? What I needed to do was turn those into instance variables. The reason that I didn't know enough earlier to do that was that 1, I didn't know who was client and who was server. And 2, given that client, given that server, was for that client there being exactly one server, 0 or 1 server, 1 to many servers, or 0 to many servers. And so basically knowing who is client, who is server, what is the multiplicity from client to server, again, this is a mechanical process. And so moving on ahead here, so 1 client to exactly 1 server, book order line to medium. There's one book order line to exactly one medium, no more, no less. And so that would be a single reference in the book order line that had a handle, a memory reference to exactly that one. Title to publisher is the same thing. In webbooks, in order fulfillment, there are no one client to zero or one server object. There are no examples of that. Basically, what that means is that you get a single reference, but you have to worry about the fact that that reference might in fact be null. Whereas if it's one client to many, like I'm a customer, how many, or title to medium, this title, Gone with the Wind, could be an ebook, it could be a print book. Then because there's at least one up to many, it has to be a collection, an array list, some kind of collection class, but I know that collection will never be empty. Whereas if it's a zero to many, like customer to book order, then it's a collection of references, but I have to worry about the case where that collection could in fact be empty. And so again, taking this forward, do you see how the shading here shows that for those I am client, you are server, for one of me client, there is one to many server objects or zero or one server object, et cetera, et cetera. You see how it's relatively straightforward to be putting in the references. Oh, from here to there, from here to there. Just want to quick point out that between medium and title and between publisher and replenish order, notice that they're dually linked. The medium references the title references the medium. The publisher references the replenish order references the publisher. They're doubly linked there. That will become a little bit significant later. Okay. So now the point is that I know the classes, I know the operations, I know the parameters, but I don't know the types of the parameters on the signature of the operation. But literally, this is going to be obvious because the parameter is there in the signature because it corresponds to some underlying instance variable in the implementation. So the most straightforward thing to do would be to use in the signature the same data type that it's implemented underneath the covers. Okay, and so print medium stock level is an int, so any function, any operation involving stock level of print media, the data type in the operation should be an int. The subject of a title is, we've chosen type string, and so anything having to do, any operation that has parameters involving subjects should be of type string. Now, of course, there are exceptions possible. Just because the underlying implementation has it represented with this data type doesn't mean that the operation signature has to be exactly the same data type. It's more convenient when it is. The code is simpler, but it doesn't have to be that way. And when it's different in the signature and in the underlying representation, it's still not a big deal where automatic types or type conversion is supported, like float to double, et cetera, et cetera. But if it's not an automatic, if it's different and there's not a built-in automatic type conversion, then I'm going to need to write a little code to be doing that type conversion. But presumably I had a reason to do so. So the point I want to make here is that now I have filled out, okay, here is the class, here is the operation, here is the signature with the name, the parameters, and their types. And I know the types now, and as well, I have the contracts. And so I'm well on my way to code. And so do you see now, the last step, literally, is that I already have the classes, I already have the operations, I already have the data types of the parameters, I have the signatures, and I have the contracts. And so the point now is to be selecting algorithms in the detailed design in the code. What algorithm is going to implement that contract? And so I might be looking at algorithms based on runtime performance, accuracy of the answer, precision, complexity, et cetera, but we need to make a selection of an algorithm and then just fill in the code, fill in the method code, having chosen that algorithm with those data types, with those parameters, et cetera, off we go. Now, we don't have time to go into it now, but there's an approach called programming by intent. It has also been called in the book Code Complete by Steve McConnell. It is called, oh crap, I suddenly forgot. Yeah, sorry about that, but it goes by a different name in that book, but it's essentially the same thing. And again, if I have an operation that's dealing with these doubly linked associations, if part of the action of the operation is to delete the link on one side, it needs to make sure to delete the link on the other side. Otherwise, I have hanging references. So just watch yourself, be a little bit careful. Okay, pseudocode programming process, and Code Complete is called the pseudocode programming process. I just think programming by intent is a little bit more clear. It's essentially the same thing. There's some minor differences. Don't worry about it. Okay, and so if I look at a specific class of a specific operation, the one that had to do with a book order being placed, then I knew its signature was the name of the event is place. It has a parameter, which is an address, which we know because of other things that its data type should be address. And we said that it required that the state of the book order be open, so that's required, and that the address is consistent with the range of the attribute shipping address, and that it guarantees that the shipping address attribute is now set to the address parameter that got passed in, and placed. This event placed has been signaled for each of the order lines in that order via the for association. And if this order had any print medium, then it was a now placed order. Otherwise, it was a completed order. That was all contract stuff that we had exposed earlier in the previous steps. But you see, the algorithm is actually fairly straightforward. Set the shipping address to the AN address, call an internal function mark as placed, which signals the place to each of the lines in the order. Then if I have print medium in this order, then I set the book order state to placed, and otherwise I set it to completed, and I'm done. And so the shading there in terms of executable algorithmic code satisfies the contract. Now, notice there's not actually a whole lot of big difference between the contract and the code. And that kind of happens fairly commonly because these operations, the contracts are so straightforward because of doing the semantic modeling. However, that's certainly not always the case, that given some contract, the implementation of that contract could in fact be quite complex. Okay, and I just want to point out the idea here of literally self-coding documentation. Our problem number 5 in terms of maintainability of the code over time is that code cannot be self-documenting, because I don't always know why the code is, what the code is supposed to be doing and why the code looks the way it does. The point is that the semantic model, as you see, through 6 of these 7 steps, was essentially telling me what the intent of the method level code needed to be, from class to operation to contract to method implementation. That's the intent of this method, and it's really obvious. And so I end up literally with self-coding documentation. Because the semantic model said this, clearly the code needs to say that in order to implement that semantic. Now, I just want to say that at this point, we've got an initial implementation that should be functionally correct. It may not be high performance enough. And so there's a whole other discussion that would take a couple of hours of taking that initial implementation as input. How can we optimize it? So here's a process for doing the optimization, but then different kinds of specific optimization techniques that can be applied. Applying at the level of splitting and merging classes for performance. In terms of semantics preserving transforms, if you will, inverse refactorings that are trading space for time, trading time for space, transforming loops and logics and procedures and expressions, optimizing SQL if that's important. I could, in fact, design and implement in a lower level. Like I got a Java implementation, but hey, suppose that for performance reasons, I cannot implement this thing in Java. Maybe I want to implement it in C. I'll show you that in just a moment. Runtime environment operations, having to do things like optimizing the operating system, the database, the network, etc. Optimizations involving things like getting more powerful hardware, going to distributed computing, parallel computing, et cetera, et cetera. Those are all candidate optimizations that we're glossing over. I just want to get the code running, functioning. We'll optimize it later. Okay, and this is a quick run through from top to bottom of, okay, I generated a Java design, but I need to implement it in C. Then by following this sequence of steps, that are expounded in more detail elsewhere, I just want to point out it's a very straightforward process that just because I had objects, classes in the semantic model does not mean I have to implement in terms of an object-oriented programming language. It's a very straightforward, very systematic process. Take semantic model as input, and I get C code as output. There's a whole lot of detail that we haven't talked about. Clearly, I'm just trying to get the high level across. How do I decide what to automate, what not to automate? We didn't talk anything about the interfaces view controller. We didn't talk about if I'm sitting on top of a database, there's something called data access object pattern that becomes relevant. If I don't want to always push events and pull data, and I want to go into more asynchronous kind of designs, how do I do that? Well, that's a whole another discussion. We didn't talk about defensive programming and how that changes contracts. We didn't talk about error handling. We didn't talk about connecting one domain to another, et cetera, et cetera. So these are all advanced topics that we did not cover here, but are certainly relevant in turning a semantic model into design and code in the general case. So let me quick wrap up. Remember, we had our top 5 root causes: vague, ambiguous, incomplete requirements. The semantic model is intentionally unambiguous, precise, concise, and the completeness guidelines and checklists and simulation minimize incompleteness. And that was really the message of the part 2, with the point being is that we're solving that problem in point 2. That's not a part 3 problem. It's not this discussion. We've already solved that problem before. The number 2 problem having to do with project management issues. This does not directly solve those problems, but if you go again back to part 2, we talk about how we indirectly solve some management problem. Management of projects that are using semantic modeling is easier than mainstream projects for reasons discussed elsewhere. But since it's not a direct solution, I'm not talking about here. Problem number 3, root cause number 3, unmanaged design and code complexity. I get complete separation of business complexity. What is the semantics of just order fulfillment? That's rather complex. And that's all in the semantic model. The technical complexity, well, that's in the design and in the code, but I can easily separate them. I get technology abstraction decoupling. I get the encapsulation of the implementation of a method, the method implementation from the operation. So that's all focusing on solving this number 3 problem. Complexity blows up in my face. Overdependence on testing. I got completeness guidelines, checklists, simulations, avoided. Again, this gets mostly to earlier, where we were talking about part 2. Self-documenting code is a myth. Again, the key here that we talked about, hopefully you realize how this self-coding documentation prophecy is becoming very clear. Because the semantic model looked like that, then clearly the code pretty much has to look like this. The semantic model is providing the intent of the code. That's why the code, normal code, is not self-documenting because you can see what the code does, but is that what the code was intended to do? The semantic model tells you the intent of code in model region. There's some other things that we can just gloss over for right now. Again, this is all extracted. This is all out of this book, How to Engineer Software. Part 1 and 2 presentation, the part 1 and 2 webinar is really focusing in on part 2 of this book, where what we were talking about today in part 3 webinar is really focusing in on part 3 of the book. And so if you want to get into more detail about how all this stuff really happens, go read part 2 in the book, go read part 3, how do I turn a semantic model into design and code, in much more gory detail, where we talk about all those topics that I said we glossed over. So there are many ways to translate a semantic model into design and code. Many of them are object. I can take this semantic model, I can turn it into C code if I want. I can turn it into Pascal, I can turn it into Fortran if that's what I want to do. There is this 7-step process for one way of doing it, and we walk through each of those. The key point, semantic modeling itself avoids and exposes requirements defects because of the content of the model, because of the process I use for building it, but that's all webinar part 1, part 2. But design and code are largely derivable from the semantic model. That's part 3. I've given you an existence proof of here's at least one way, and kind of hand wavy another way for taking it into non-object oriented C, Pascal, Fortran, COBOL, if that's your game. That's from the design and code perspective. And remember that code is a mapping. And when that mapping preserves the semantic, then the code is correct. And again, I just want to reiterate that self-coding documentation thing. And so the goal today was to show how design and code can be derived from semantic models. Hopefully you saw how straightforward a process it was for the most part, and illustrating more the value of semantic modeling. Parts 1 and 2 webinar were all about the value of semantic modeling from a requirements perspective, and now we're looking at the value of the semantic model from a design and code perspective, because if the semantic model didn't lead directly to design and code, then it really wouldn't be all that valuable. But showing now how it really does lead pretty much directly to the design and code, hopefully builds on the requirements value of the semantic model, showing you the design and code value of the semantic model. And so if you want to track down references, here they are. I'm all done. And so what I'm going to do now is I'm going to turn it back over to Jesse for questions that may have come in, and we'll answer questions as best we can. So go ahead, Jesse.
Hey, Steve. First, thanks for the presentation today on a tricky, very deep topic. We actually didn't get any live questions today, and we've gone a bit over the hour. So I'll just make a note to people that are still out there. If you did have a question that you weren't able to ask, feel free to reach out to us via email. You can simply hit reply to any of the emails that I've sent, and I'll forward those along to Steve. So we can go ahead and end it there. I think you were very clear today, Steve, and really appreciate you taking the time to do this webinar today.
Okay, thank you. And oh, by the way, do remember that down in the description will be the link to a complete semantic model and a complete implementation in Java from that semantic model. And you can compare side by side and look at what I was talking about here from a more complete perspective. So
that's great, Steve. And I'll make sure to include that in the email that goes out with the recording too. So thank you.
Great. Okay, thank you, Jesse. Thank you, everybody, for taking the time, and hope to talk to you again in the future. Bye.